Here we have a question about Rolle's theorem. We have four functions, and we would like to know for which one we can apply the conditions of the theorem to get its consequences. So usually with every theorem or every result, there is a set of conditions they need to satisfy in order to have the results of the theorem activated. So it's like you have to specify certain criteria for certain things to happen. So if this and this and this satisfied, then you will get that, that, and that. So let's recall together what the Rolle's theorem was all about. So this is the statement of Rolle's theorem. It says that if you have a continuous function on some interval AB that is differentiable on the open interval, and you have that f of A is equal to f of B, then there is a C at which the derivative, so not the function, the derivative is equal to 0. And let's try to briefly make sense of this. So now I will construct a function which satisfies these properties. I have here f of A and f of B on the same level. So this is f of A, and that is f of B. Now let me draw my function. Maybe I'll draw a very simple. Yeah, so this is a very simple function. And what's the theorem saying? It's saying that there's a point at which the derivative will be 0. But what's the derivative again? It's the slope. Slope of what? Of the tangent line to the point in discussion. So here I've chosen it very nicely to be here. So the derivative is this, the tangent line. It's this one. And I want you to notice that here the slope is 0. If you have a line that goes like this, it's not increasing, it's not decreasing. And so the slope is effectively 0. So all that it's saying is, if the function is continuous, so you can draw it without lifting the pen, and it ends up landing at the same point at the end, then probably there is a point where it was increasing and then it became decreasing. So it will also look like this, for example. Because if it keeps decreasing, right, then it will never reach f of b. And if it keeps increasing, let's say it's increasing like this, it will never reach f of b. So that's at least some sense. You can think of a rope that's fixed to these 2 points and keep doing like this. All good visual images. And the slope is effectively, so slope is positive, and then a bit positive, and then less positive, and then 0, and then negative, and then more negative, and then even more negative. And there's of course the example of the constant function, so you could just draw a function that's constant that connects the 2 points. Then there is more than one c at which the derivative is 0. It's actually all functions, all points in the interval. So that's some good intuition about the problem. The key property here is that we need to have f of A equal to f of B. So perhaps that's something we need to inspect. So we start with the logarithmic function. Well, you need to know this in advance, but the logarithmic function is 1 to 1. So it has a graph that looks like this. What about x cubed? Looks something like this. It's also a one-to-one function, or yes, it is a one-to-one function in the sense that every input has only one output. And for a to the x, I'll just take a to be equal to e, because this could be any constant, but they all look more or less the same. It's still one-to-one. So as an example, this is the graph of e to the x. Something that looks like this. The end goal is really to say that they are one-to-one functions. So there is no point at which you start at, let's say, f of a, and then you circle back to the same height. And so from here we know that the answer is not going to be log of t or x cubed or a to the x, simply because there are no 2 points a and b such that f of a is equal to f of b. These are one-to-one functions. For every one input, there's only one output, and vice versa. For every output, there is only one input. So that is the key to understanding what's happening here. This is e to the x. That is log of x. These are of course not accurate and not drawn to scale. So I hope you don't come after me after this video. And this is x cubed. Okay, so we know our answer. Are we done? Well, in the exam, yes. This will be your answer. But let's do even more analysis and actually check that this is going to be true. So the first thing that's interesting about this function is that I can factorize it as follows. You get 2t squared minus t minus 1. And I'm feeling good today, so I think I'll try to find the roots of this function. And if I do, then I have, well, clearly I have t is equal to 0 as one root. Maybe I have two more that they are coming from here. Maybe not. And to find this out, I'll just use the quadratic formula. So negative of minus 1 plus or minus the square root minus 1 squared. First off, minus 1 is 1. That's negative b for you. And minus 1 squared is negative b squared, which is 1. Minus 4 times a times c, which is negative 1. So I'll just remove this minus and just put a plus in here. And then you divide by twice of a, which is 2, so 2 times 2. 4 times 2 is 8. 8 plus 1 is 9. And the square root of 9 is 3. So I'll leave this as it is. I won't simplify it any further. Okay, maybe I'll write 4 in the denominator. So this gives me two solutions. It gives me 1 plus 3 divided by 4, which gives you 1. You can also check that it's a root by plugging in 1. And you can also get t is equal to minus half. 1 minus 3 is 2, and 2 over 4 is minus 2 over 4 is a half, is a negative half. Okay, so we have more than one point at which f of a equals f of b. And so this could be your a and this could be your b, or you could choose the second one and the third one, or you could choose the first one and the third one. It doesn't really matter. The most important thing is that you have a nice setup. And the function is continuous, because if the function is not continuous, then you could just have a function that looks like this, and it's not continuous. So I can just lift my pen and then I do like this. Now, why is this function continuous? It's because it's an addition of continuous functions. So t is a continuous function, so is t squared, and so is t cubed. Well, twice of t cubed. So we can even apply the theorem here. Now, do we need to find the c at which the function, the derivative is equal to 0? Well, not really. No, this is not the goal. You can, of course, try to differentiate it. I think it would be a very good exercise to differentiate this, set it to be equal to 0, and try to find which c's give you this value, at least in one of these intervals. So let's say from 0 to 1, or from -half to 0. So that will be the answer. And I would like to conclude with the drawing of this function. So you see all the action is happening at -half, 0, and 1, because these are the roots. And notice that we have something that looks like this. So we have something from -half to 0, something that looks like this. So it is actually equal to 0 here, the derivative, at this point where you have there's no change. Similarly, if you look at the other one with 0 and 1, you have a graph that looks like this. Same thing. So this is the point at which the derivative is 0, the rate of change. Now I'm just showing you this so you can see it. And this is how we apply Rolle's theorem in general. I hope this was a good exercise for you, and I hope you learned many new things.